I wish I was like that. Next time. No, it's not. No, obviously we believe like Jimmy was such a weird person. So they told him I like never like what did you say became like sure. But then the other people had to like page back.
Okay, so let's go to page 19.
Like that. I think something. Yeah.
So we're going to go all the way back to revisiting limits. We weren't able to do this when we were going through our limits unit because we haven't learned derivatives yet. But now that we've learned derivatives, we're going to approach limits from a derivative perspective, and that allows us to find limits in a different way. Okay, but I want to connect back with what we've done in the past here. So when we're evaluating limits, the first thing we do if we're approaching real number is we always plug in through direct substitution, right? That's always our first step. We never do anything different other than that. So first things first, if we evaluate our limit here, what are we going to get? If we do direct substitution, numerator, we get 3 in for x. What's our result? 1/3. If we have a real number, there's nothing more to do, right? If we do direct substitution, if we get a real number, that's our answer. Okay. Let's try this example here. Right. First things first, direct substitution. 2 squared minus 14 plus 10. Okay. Numerator, we get what? 0. Denominator, we get 0. So this tells us, what does this tell us? That there's a what? There's a hole, but the limit, does limit exist? Yes. Okay. Limit exists, right? So we know that there's a hole, but the limit exists. And whenever we saw this, we would go through our factoring process and multiplies to be 10, adds it to be -7. The holes cancel out. We know the cos of the 0/0 has been removed. Reevaluate our limits, and we get what? What happens if we try to reevaluate. 2 for x, we get -3. Okay, so we get a real number, so we stop, right? There's nothing more to do. It doesn't matter if it's a one-sided limit. If we're getting a 0 over 0, it doesn't. We already know the limit exists, right? The one-sided limit is not going to impact us. So we now have a different method of doing this. This is still valid, but we have another option now involving derivatives. So this is called L'Hopital's rule. It says, suppose that f of a and g of a is equal to 0. So let's say we do direct substitution and we get 0 over 0. It also works for infinity over infinity, but it tends to be not as helpful because I think the method that we use right now with comparing degrees is faster, but it's more useful for 0 over 0. So if we get a 0 over 0, we call this indeterminate form. If we get an indeterminate form, L'Hopital's rule allows us to apply the following. So if you want to evaluate the limit as x approaches a of a numerator expression over a denominator expression, and we get 0 over 0, what we can do is we can take the derivative of the numerator and the denominator separately, plug in our x value, and see if that will allow us to get to a real number. Okay. If we get a real number, then that's our limit. So let's try that with the problem that we just did above. We went through the factoring process, which we know gave us a limit of -3. So if this is going to work, then we should get the same result if we're doing L'Hopital's rule. So let's approach this problem again using a different method. So same problem as example 1. I'm just putting it slightly below it. First thing we do, direct substitution, we get 0 over 0. Now, this is the only time, other than infinity over infinity, are you allowed to go through L'Hopital's rule. Okay, we don't want to jump into this process until we've confirmed that there is direct substitution gives us 0 over 0. So now that it gives us 0 over 0, we can do this. Okay, we're going to take the derivative of the numerator. So what's x squared minus 7x plus 10? What's that derivative using power rule? Okay, 2x minus 7. And then separately, we'll do the derivative of the denominator. X minus 2 becomes what? 1. Okay, so now that we have the derivative version of the numerator and denominator, we can reevaluate our limit. So now plug in 2 in for x, we get 4. 4 minus 7 is -3. So we get the same results. It's just now a different option for us rather than going through the other methods that we've learned from first unit, whether it's factoring or complex fraction or conjugate. Now we can, if we get 0 over 0, we can take the derivative of the numerator and denominator separately and reevaluate our limit. Okay, so let's see if we can try a few examples here. This is example 2. Limit as x approaches 2 of x minus 2, as x approaches 2 of x minus 2 over 3x cubed. Yeah, minus 6x squared plus x minus 2. First thing we do, regardless of whether we want to do L'Hopital's rule or factoring, we always do direct substitution, right? So I'm looking for that as well on the quiz. When you're evaluating a limit, even if you get the right answer and if you go through the right process, if I'm not seeing that direct substitution step, then you may lose a point. Okay, it doesn't mean that you have to show me that how you're plugging in every number. I just want to see that you are confirming, showing me that you're attempting direct substitution. So in this case, plug 2 in for x, I get 0. Denominator, I get 3 times 2 cubed, which is 24. 24 minus 24 is 0. 2 minus 2 is also 0, so we get 0 over 0. So you don't have to show me, how you're plugging in all the numbers, but just show me and confirm that you are getting that indeterminate form, which will allow you to move on to the next step. Now, this is tough to factor. We can actually, we see the benefit of L'Hopital's rule because it allows us to, when algebraically, when it's difficult to work with those numbers, we can just take the derivative and then evaluate the limit again. Okay, so numerator's derivative, x minus 2 becomes what? 1, okay. Denominator's derivative, 3x cubed becomes 9x squared minus 12x plus 1. Now that we have our derivative, we can reevaluate our limit to see if that will get us down to a real number, where before it was getting us 0 over 0. We knew a limit existed, so we should be, we never want to stop at this point, right? We know that this is kind of an intermediate step. We know that there's something, a real number waiting for us. So we can reevaluate our limit, plug 2 in for x. We got 36 minus 24 plus 1. Okay, that gives 36 minus 24 is 12. 12 plus 1 is 13. 1 over 13 is a real number, so we can stop. Any questions here? All right, we're gonna skip 3 and 4. We haven't done trig yet, so we'll save all the trig topics till the end of the semester. Okay, number 5 here. When I see infinity, I typically want to use the older method that we've learned. I think those are more efficient, they're faster. And if we see infinity, what do? We compare what? Compare degrees, right? Oh, as long as there's degrees to compare with. Here, these are different families of functions. You got x squared, you got e to the 2x. And if I see infinity, I'm either going to compare degrees, or I'm going to do comparative growth rate. And comparative growth rate is where we know that if we're approaching infinity, that these families of functions are all growing at predictable but different rates. Logs are slowest, radicals next, polynomials, exponentials. And here we have a polynomial over an exponential. E to the x is considered exponential. So I have a slower over a faster. You guys remember, what does that turn into? 0, yeah. So it's either 0 or infinity, depending on which one is faster, right? And because the slower is faster, the top is fast, the numerator is slower, the denominator is faster. We know that fraction is getting smaller and smaller, it's heading towards 0. So I typically don't do L'Hopital's rule if we're doing infinity. It just feels faster if we just use the rules that we've learned in the past. But I do want to show you that L'Hopital's rule does work involving infinity. Sorry, we haven't quite learned the derivative rule for e to the 2x, but I just want to kind of show you here. If I plug in infinity, I get infinity over infinity. Technically, that's indeterminate form. So the derivative numerator is 4x. Let me just show you the denominator of the derivative denominator is 2e to the 2x. If I plug infinity again, I'm going to get infinity over infinity. And then derivative again, if I get indeterminate form, that gives me another option to do, or gives me the ability to do L'Hopital's rule again. Derivative of numerator, we get 4. Derivative of the denominator, we get 4e to the 2x. And now if I plug infinity in, I get 4 over infinity, and that should basically tell us, okay, if I have 4 over infinity, that denominator is infinitely large, which makes my fraction go to 0. So my suggestion is, if we see infinity, let's go through the older method. It's just faster, more efficient. But if we get 0 over 0, then let's explore the possibility of L'Hopital's rule, because that can be a more efficient way than going through all the factoring cleanup steps that we've learned before. Okay, final thing that I want to, before we do more practice, is that L'Hopital's rule is not a replacement for quotient rule. Right? I know that this derivative process feels easier because, oh, it's nice to just find the derivative of the top and the bottom and not have to go through the whole f prime g minus f g prime. But we only do L'Hopital's rule if it's in the context of a limit. Okay, normally we can't just do numerator and denominator. So this, okay, I know we can't do this trig. We haven't learned that yet. But let's say the function was x squared minus 2 over 2x minus 5. Okay, we can't all of a sudden say, okay, great, I'm just going to do L'Hopital's rule here, and my derivative is just 2x over 2. Okay, we can't take the derivative of top and bottom unless it's within a limit context, right? If I want to find the derivative of this, I still have to go through f prime g minus fg prime all over e squared. So we don't want to get these two processes confused with each other. L'Hopital's rule is great if it's in limit limit problem, limit perspective, where we can do the derivative of top and bottom separately if we get 0 over 0. But if we're just asking for a derivative of a function, we still have to go through quotient rule if there's a numerator and denominator. Okay. Let's see. All right, next page. There's only a few problems we can do for the next page. So since a lot of this involves functions we haven't learned derivatives yet. So we'll try 1, 2, and 4. Okay, so go ahead and try those problems. Remember, your first step is always direct substitution, right? And show me that you're getting, if you're getting a 0 over 0, that gives you the green light to do L'Hopital's rule once. If you get a real number, then that's your answer. If you get 10 over 0, then the limit doesn't exist, right? We only do L'Hopital's rule if there's a hole in the graph, only if there's a 0 over 0. Bonuses. Bonuses. Someone's music is playing. Hopefully it's not too distracting. Okay, so I want to see that 0 over 0 initial step to confirm that we do have the prerequisites, the requirement needed for L'Hopital's rule. We do get that. We do get that 0 over 0. So now reevaluate our limit. Going through L'Hopital's rule. So the top, we do power rule. Denominator, we do power rule. And then we reevaluate our limits. Rewrite your limit statement again. We get 1 over -1. That's a real number. So that's our answer. Okay. Try number 2. Okay. And then try number 4. I do want to point something out here. I don't have an example of this, but at least I can talk through it. What if you go through L'Hopital's rule? Okay, assuming you get 0/0, and you go through L'Hopital's rule, you revalue your limit, but then you still get 0/0. What happens if you get 0/0 after you do L'Hopital's rule? What do you think we'll do there? Take the what? Do the derivative again. Yeah, so you can do L'Hopital's rule a second time if you get another set of 0/0. So each time you get 0/0, you can do L'Hopital's rule once. You can do the derivative process once. But just make sure that as soon as you do the derivative, that you do direct substitution right after that. That you don't just keep finding the derivative over and over again, because that may lead you down the wrong path. So just make sure that each time you get 0/0, you can do L'Hopital's rule, take the derivative. If you get 0/0 again, do L'Hopital's rule a second time. But as soon as you do the derivative, make sure you follow that up with direct substitution to see if you are sitting at a real number. Okay. And that's basically it. It should feel like a easier process than what we did in the first unit, where we have to go through a lot more options, or learn a lot more different ways to clean up, whether it's factoring or conjugate method or complex fractions. Now we just have this option of just one process, right? Take the derivative, reevaluate, see if you get a real number. All right, let's see what we can do next. And this shift over to the 2 handouts that you picked up. Let's start off with a particular Pythagorean theorem problem that I want us to see. And this is okay. Let's go to page 5. Page 5 in your quiz review. Okay, so balloon is rising vertically above a level straight road at a constant rate of 1 feet per second. So we have the balloon rising. And when it is 60 feet of 5 feet above ground, a bicycle moving at a constant rate of 17 feet per second passes under it. So how fast is the distance between the bicycle and the balloon increasing 3 seconds later? So we have the balloon here. We have the bicycle here. And we're trying to figure out what is the rate of change between them 3 seconds later. Okay, so this is the Pythagorean theorem problem. I'll call the horizontal component x, the vertical y, and the hypotenuse z. So just like before, our derivative is going to be pretty straightforward. X squared plus y squared equals z squared. Find the derivative. All the time components show up. So x squared becomes 2x dx dt. So derivative is the easy part. Trying to figure out all the different values is a little more challenging here. Okay, so let's see if we can list out all the variables. There's 6 variables that we have to account for. So x equals, y equals, and z equals. Okay, so the balloon is rising, the bicycle is moving, and the distance between them is also increasing, right? So all these dx, dt, dy, dt, dz, dt, these are all moving, and these are all getting growing, right? All those values are growing over time. Okay, let's see if we can pick out some of these values here. Okay, the balloon is rising at a constant rate of 1 feet per second. Okay, what can we assign that value to? dy dt, right? Well, vertical motion is I've defined it as y. So rate of change, there's a time component, positive or negative. Because, well, not because it's going up, because why? What's happening to y? Y is increasing, yeah. So I don't want to have us assume that just because it's, in this case, yes, it is going up, but sometimes going up may end up causing that vertical distance to decrease. Okay, so we don't want to ever depend on the direction. You want to consider what's happening to your length as time passes. Okay, good. All right, just when the balloon is 65 feet above ground, what is that? What's that referring to? Y. Okay, I'm going to put that temporarily because this may change, but we know that for the moment it is y related. Okay, we'll keep going here. A bicycle is moving at a constant rate of 17 feet per second and passes under it. What's 17 associated with? The xdt, okay. Positive as well, because not because it's moving right, but we can expect that x value to continue to grow as time passes. Okay, so 17 feet per second. Right. How fast is the distance between the bicycle and the balloon increasing? What are we looking for? dc/dt, yeah, that's the unknown. Okay. 3 seconds later. Okay, 3 seconds later. So let's think about where these where the x and y's are, and even z, 3 seconds later. So that means 0 seconds, the bicycle is going to be directly under the balloon. Where do you think the bicycle is going to be in relation to where it is 3 seconds later? How can we find that? Good. We know how fast it's going, right? So after 1 second, it's going to cover 17 feet. Another second, it's going to cover another 17 feet. Another second, it's going to cover a third 17 feet. So 3 times 17, we can get 51. So that means 3 seconds later, if he's moving at 17 feet per second, 3 seconds later, he's going to be 51 feet away from under the balloon. Okay. Now, the tricky thing is 3 seconds later, is the balloon going to still be at 65 feet? Okay. It's still moving, right? It's 65 feet the moment when the bicycle passes under it. So 3 seconds later, if it's going at 1 feet per second, where is it going to be? 68, right? So each second it's inching upward 1 feet per second. So after 3 seconds, it's going to go up another 3 feet. So 3 seconds later, if we're taking a snapshot of this scenario, this balloon is going to be at 68 feet above ground. Right, so that's the hard part. The hard part is realizing, oh wait, the balloon is still moving. That 65 is not our final value. We still have to make adjustments to it because it's not asking about at 0 seconds, it's asking about 3 seconds after the fact. Okay, so Z now we can go through what to find Z. Pythagorean theorem, right? A squared plus B squared equals C squared. So once we find that value, then we can plug everything in and solve for dc dt. Okay, let's try that. Try that. You can also check the key a few pages later on page 9. Everything is positive. My dx/dt is positive. My dy/dt is positive. So those are easy numbers to plug in. We use our calculator, and we should get a dc/dt of a positive 11. That makes sense as well. That as the balloon keeps rising, as the bicycle gets further and further away, we can expect that rate of change between the balloon and the bicycle to continue increasing with at a positive rate. All right, any questions here? Okay, I said that I wanted to do a cone problem each day. So let's go back to a cone problem because that is the one that takes the most amount of steps. So this is the help sessions review handout. So can we turn to that and try number 1? Go ahead and try it. Maybe I can pull a similar problem from before where you guys can match the steps, but the key is also directly on the next page. I just want to see as you guys try it, second and third time, that it feels like it's that the steps are connecting better on your own. So let's just see. So this is help session review. I pulled this. This is the first one that we did as a reminder of the steps, but I want us to do number 1. Okay, so we set up our proportions. We should be able to get this part. R over 5 equals H over 12, right? Cross multiply, we get 12R equals 5H. We still don't know exactly which variable to solve for, but we can put that on hold and gather more information from our problem. So we know that water is flowing out of the tank. So we know dVdt is going to be a negative value. Want to find out the rate at which the water level is dropping. That's talking about the height. So we're looking for dHdt, right? When the radius is 4 feet, okay? And we're going to put a box around this 4 feet because we know that this is a moving value, right? That 4 feet is not going to play a role until the end of the problem. If you start plugging 4 into your ratio, then you're declaring to the problem that the radius of the water level is never changing. We don't want to we don't want to use that value yet. We want to hold on to that variable. It's still a moving value. But we are going to involve that 4 at the end when the derivative process is complete. So we do want to save this until the end to use. Okay, do not use that 4 too soon. Okay, so but the big hint is this dHdt, right? If we're looking for dHdt, then we would prefer to have our equation in terms of what variable? R or H? dHdt is related to which variable? Height or the radius? Height, right? So we want to try to get our H variable showing so that we can produce dHdt, which means that we can try to remove the radius. Okay, find a way to replace the radius. So we go to our volume formula, V equals pi over 3 R squared H. This will be given to you. You want to find a way to replace the R because we don't need dRdt, we want dHdt. So I want to find a replacement for R, so that's why I'm going to solve for R here. So R equals 5H over 12. Take my substitution. R gets replaced with 5H over 12. I square everything. I get 25 H squared over 144. We've kind of seen these numbers before, right? Multiply everything through. We get 25 pi over 432 H cubed. And now that we're here, we can move into our derivative step, right? Everything is nice and clean, no parentheses, no multiple variables. Everything has been consolidated. So now we find the derivative. 25, the coefficient stays. H cubed becomes 3H squared. D becomes dVdt. H becomes dHdt. And now we can start plugging in values, right? dVdt is negative 12. dHdt is what we're looking for. So it's nice to see that variable here. But do we have the height of the water level? What do we have though? We have the what? We have the radius of the water level. So how can we get from one value to the other? Is there something that we can use to help us connect those two values together? We have this equation, right, that we created using similar triangles. So now if I can plug 4 in for R, I can work backwards and solve for H. If I solve for H, then I can figure out the height of the water level at this moment in time when the radius is 4. So I'm going back to my fractional equation, and I'm solving for H, and I end up getting that H being 48 over 5. Once I get that 48 over 5, then I'm off to just trying to clean all this up. Multiply everything through. Hold on to the pi. Don't plug pi in the calculator. Once you get everything cleaned up, if you divide it over, it's going to end up in the denominator. If it's in the denominator, it needs to stay there at the end of the problem. I just plugged the 12 and 16 in the calculator and saw that it reduced to be negative 3 over 4. Okay, any questions? Okay, let me talk about the schedule. So no school tomorrow, which means I'm going to be pushing the quiz to next Wednesday. Okay. So Monday, we'll do a full quiz review. Tuesday, we'll still do quiz review, but I don't want to lose a day of instructions. So I'm going to start 5.1 notes, the first half of class, review second half of class. And then that way we have a class period and a half to prepare for your Wednesday quiz. Okay. I got help sessions on the board there. Monday afternoon, 3:30 help session. Tuesday morning, 7:30 help session. And then Wednesday, the day of your quiz, 7:15 a.m. help session. We've learned everything that we need to learn. So if you want to start working through practice problems on your own, you guys have the packet, you guys have the keys. So hopefully you guys can pace yourself and do what you need so that next week, if you have specific questions, you can get those answered before your quiz. Okay, so we'll do a full quiz review on Monday and part of Tuesday. All right, come get your phones. I'll send out a reminder about those help sessions on Sunday.